Hello, welcome to Projects Euler number 3, and today we will be finding the largest prime factor of this enormous number. Um, and here's the official question, so it gives us the prime factors of 13,185. We can clearly see 29 is the biggest. So the question is, what's the biggest prime factor of this massive number? And I'll just read it out for fun. It's 600,851,475,143. I actually got that right. Great. So I've kind of outlined an approach here, just because I'm slow at typing. I've just written it down beforehand. So we're gonna find all of the factors, then we're gonna keep the ones that are prime, and finally we're just gonna keep the biggest. Now I've done similar things to this with finding factors, and I looked at the code I did for it, and it was just a bit much, bit much for me to understand. So I'm kind of just going ahead and doing this rather simple approach here. Alright, so let's think about first, how do we find the factors of a number? And let's just, I guess, naively suppose that our number is 100. I think about how you find the factors for that, so I'd probably just start out with going from 2, 3, 4, 5, seeing if they divide 100. If they do, that's going to give us a sort of pair of factors. So you'll end up with sort of 250. 3 doesn't go. You'll then end up with 4 and 25, so on and so forth. But what you kind of realise is if you go over a critical point, then you'll kind of start reproducing these pairs. So the next one's 5 and 20, right? And then I think the next one is it divisible by 8? Nah. And the next one's going to be 10 and 10. And then the next one after that is actually going to be 20 and 5 again, right? If you keep going up. So what this means is once you've gone past the sort of the square root of that number, you basically get the same pairs you've already got but in reverse. So what that means is you only need to consider taking sort of test numbers below the largest, below the square root of that number, right? So that means that if the number we were looking for finding the factors of was 100, we'd have to do 10 iterations, because 10 is the square root of 100. For this one, we'll have to do whatever the square root of this is. I think it's 6 times 10 to the 11, isn't it? 12 digit, yeah, 6 times 10 to the 11, alright, and that's perhaps better known as 60 times 10 to the 10, and if we take the square root of that, that'll be the square root of, I guess, 60 times by the square root of 10 to the 10, which is better known as 10 to the 5, like that. And then I reckon the square root of 60 is going to be 7.8 or something, just because 64 is the nearest square number. So we're looking at about 700,000 iterations to get all of the factors for this number, and that's fine. We can do that. Easy. Alright, so why don't we go ahead and write the code for finding all of the factors for this number. So let's call it something vaguely sensible, get all factors maybe. I'll take a number, and that number's going to be, I guess, a long. And I'm not really sure what we're all saying yet. Maybe it's probably going to be an iterator, isn't it? Let's be honest. I love iterators for whatever reason. And then we're basically going to do that whole, I guess, we want to find this max factor thing, which I think it's a makeup brand, isn't it? Max Factor. But we want to find this max factor, and it's just going to be the square root of n, essentially. But there's always going to be some ceremony around square rooting numbers that are sort of not in the right thing that makes them square rootable. So you can only really square root a double, then you can turn it back into a long. And then, just for good measure, I'm going to add a 1 on, just because, iterators, you've got to go, 1 beyond where you want to be, which is great. And then I guess our iterator is going to be we're going to do range, we don't care about 1, so let's start at 2. There's our max factor, that's the sort of upper bound. And then I guess we kind of want to sort of map it over to the pair of factors. But because it's a pair of things, this kind of makes me think what we actually want is kind of a 4 comprehension, so let's go ahead and do that actually. Um, you'll see why in a sec. And if you don't know what a for comprehension is, I will explain it. So we're going to take like our sort of x from right over here, like this. These are like our test things that we're going to try dividing by n by. And then we're going to say like, and I'll explain the syntax later. If n is divisible by x, so as usual, the remainder operator from like the first two problems, I think we've used it now actually. I guess it's quite a useful thing. We're going to do that, and then we're going to get a factor from this kind of iterator here, and this iterator is just literally going to be n divided by x and x itself. So that'll kind of give us like the factor pair. Ooh, that's sort of floating around, that autocomplete for us. And then we're going to yield out the factor like that. And format her, there she is, nice. So what this for comprehension does in general is like, I'm going to take a thing from here, and I'm going to take a thing from here, and I'm just going to return this. That's a really bad explanation, but they're like list comprehensions in Haskell, I guess. Oh, and I've realised, actually, that's not going to be particularly happy because iterator.range only works for ints. But not to worry, we'll use iterator.iterate. We shall start with 2. We shall add 1 on like this. Start with 2 as long actually. And then what we're going to do is we're just going to take while it's, I guess, less than the max factor. That's kind of equivalent, right? So it's gonna, so this will go like 2, 3, 4, blah 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 blah, until it hits this. Great. So, oh yeah, so I was gonna try and explain a for comprehension, I guess. So, yeah, like a list comprehension in Haskell, but it's just a way of sort of combining lots of elements from different iterators, from different lists. Anything that that has something called flat map defined on it, actually. It's just syntactic sugar for doing loads of flat maps in a row and doing a map at the end. But the point is, this is going to give us a lot of factors in a sort of flattened out list rather than a list of pairs, which is what we want. And I don't even have to modify the return type. That just seems to work. Alright, so this will get us all the factors, just not necessarily the prime ones. So the next part of this problem is to consider how to get ourselves a way to test if a number is prime or not. So I think the way that we can do that is, oh, that's actually sort of, let's just move this into its own little scope, because we like stuff there, don't we? Alright, so one way to do this whole prime thing is with something that's rather similar to an iterator, but doesn't get consumed when you look at it again. So the thing about iterators is like, if you sort of look at one, if you consume one, it ceases to exist. And what we're going to do is we're going to use something called a lazy list to give us like a list of primes, and then we're going to basically just define an isPrime function that'll go through that list and see if your number is divisible by any of the primes in that list. And that's how we're going to define primality. Is this the most efficient way? No, but it kind of makes sense. And it's actually really similar to what's going up here. Like, there's loads of better ways of finding prime numbers. This is just kind of the simplest I can think of. So it starts with like a lazy val called my primes, like this. And because we're using longs everywhere, I think that this should be longs. And the reason, by the way, that we're going to have to use longs is it might be the case that this is like, the biggest prime is like this times 3. It probably isn't, but that would definitely be a long rather than an int. So we have to make sure to use longs, otherwise we're going to get some like weird integer overflow business, which like ain't nobody got time for that when doing a project Euler problem. So lazy lists, I think they used to be called like streams in Scala or something, but it's got this kind of weird ass syntax where you can just do this sort of thing. So 2 is going to be my first element, it's the first prime number, shockingly. And then to get the other prime numbers, we're going to use very similar to iterator.iterate. We're going to use sort of lazy list to iterate, which does, it's the same kind of format. We know that all prime numbers are odd, so we only need to actually check like odd numbers. And like I think there's even a way of doing this where it's like stuff that's either one above or one below multiple of 6, but like I can't be bothered with that right now. And then we're going to filter them to be the ones that is prime. Obviously, we've not defined as prime yet, so why don't we go ahead and define it? So something is prime, along is prime, and that's obviously a billion. Yeah, I generally like to just give out the type annotations. I think it's just a habit from work, to be honest. Like, the types actually carry a hell of a lot of information, especially if you're working with big old clunky types like your crazy ass monadic types. Alright, so then we're gonna do this take while the square root take while the prime squared is less than that number. For this exactly the same reason we take the square root up here, where we're doing this. And I'm kind of surprised that we're getting a sort of angry there. I think it's because it doesn't know that this is meant to be. Yeah, interesting. Take a while. Yeah, I kind of thought this would just work, but let's see. Let's see what's wrong. And then we need it to be that for all of those, when you divide it by your prime, when you divide n by each of your prime numbers, it needs to be non-zero, obviously. Okay. Because so you're testing that n cannot be divided by all of the prime numbers. And I'm really not sure why it's getting so upset about this, because take a while. Prime stop. No, I know why it is. It's because this is like going to be sort of, well, lazy list of longs, but I think it's a bit confused maybe because that's not a long. Yeah, there we go. Problem solved. Yeah, like, I'm not a massive expert in how Scala compiles. So anyway, we've got this is prime function, and this will always work because this lazy list will basically generate as many primes as is needed to determine if n is prime, because it'll generate them until this condition holds, right? When we're actually evaluating the primality of something. All right. So why don't we go ahead and I guess get all of the factors of. We'll do it on that test number first, actually. I can't remember what it was. It was like 13,000 and something, wasn't it? 13,195, great. 13,185, like that. So we can get all the factors of that. It'll get coerced into a long when this sort of thing happens, whatever. And then we can filter them to be as prime. And remember, this is an iterator, so it's not going to do that much. It's not going to sort of print it out for us, because it'll just be well, you've not sort of tried to collect me or anything, so I'm not going to do anything because I'm lazy. Iterators are literally the laziest thing in the world. Alright, so let's go ahead and evaluate this and see what happens. Alright, so it looks like it's given us 5, 7, 13, and 29, which I think is what it was. Yeah, how about that? And it's taken 150 milliseconds, which is pretty sweet. So I guess the last thing to do is do .max instead of .list, toList even, because do you know what? Let's do toList. Let's have a look at all of the prime factors. It might be interesting, or it might just be loads of them. Well, we're gonna find out, and we can kind of get rid of that and just make that our thing. And alright, let's go ahead and. Alright, well, looks like it's finished in, I guess, about twice as long as the previous one took. And it only has 4 prime factors apparently, and the biggest one is clearly this one. So why don't we go ahead and see if this is actually the right answer. Let's see. Alright, I'm not very good at these capture things, I always confuse my 7s and 1s, and I forgot a 6 there, didn't I? Alright, let's see. Yeah, there we go. Alright, I guess that's kind of the end of this one. So to recap, what we did was, all we did was we got all of the factors for a number using this sort of algorithm. It's not really important. Yeah, it's not really fancy enough to be called an algorithm, I suppose. And then we just filters them to see if they're prime using this kind of weird construct I got down here, which again is just a thing that makes a list of mostly odd numbers with the exception of two, to make your primes, and then to test if something is prime, you take all of the prime numbers that are less than the square root of that number and check that for all of them they cannot be divided exactly by n to give a remainder of 0. And that's kind of the definition of primality. Like I said, this is not the most efficient way of doing this problem at all, but it works, and, conceptually I can kind of get what's going on here. I can kind of understand this. I mean, I did just write this, so obviously I understand it as I've written it, but you know what I mean. And yeah, I think that's it. As usual, if you did stay till the end, thank you very much for watching, and hopefully this was better than my last video, which is something I'm saying a lot now. And I will see you for problem 4, whatever that is. Right, see you later.